Okay, let's start. Hello, everyone. My name is Ignat. Thank you for coming to my session. And today, my session is less of a developer talk, which you might have seen elsewhere today, but it's more about uh, managing Linux kernels in production. So, anyone here is not a developer who manages something in production? Or anyone has a Linux computer at least? Yeah, good. Okay, so the talk is an engineer's guide to Linux kernel upgrades. So, first a little bit about myself. So, I'm Ignat. I work for Cloudflare. Who here doesn't know Cloudflare? Who here uses Cloudflare? Oh, good. Thank you very much. Who here pays for Cloudflare? Still using Cloudflare is great. Thank you very much. So yeah, I do Linux at Cloudflare, so I'm responsible for the Linux operating system we run on production. I'm also interested in system security and performance, and I also do low-level programming, so mostly like kernel stuff, drivers, bootloaders, and other stuff written in C, not even C++. Okay, but to just be awake a little bit. So what do you do in this case? So imagine you're doing your work, like days go normally, and then suddenly you have this pop-up. Updates are available. Who will press install now? Okay. Who will press later? Well, I assume everyone else, right? People who said they'll press install now, would you do differently if it was a production system? Would you press install now? Yeah, so in production, updates are not great, right? So it's either when we see updates, whereas defer them or just try to completely forget about them. And this is natural because it kind of connects us, like how do we perceive software updates, right? So especially in production systems. And the reality is we don't like them. We don't like software updates because these are kind of external dependencies which may bring chaos to our perfect environment, right? We don't really control, so something in the code can change and accidentally break our system. Why would you install software update if everything works fine, right? But there are different types of upgrades, and just for regular software update, yes, we don't like them. We see them as some kind of a monsters, but they're not like scary monsters. They're like more like annoying, ugly monsters, which make our life a little bit harder. However, if it comes to Linux kernel upgrades, the perception is much different, right? Because we see a kernel upgrade, especially in a production system, as something really scary. It's that all of destroying monster which can destroy our universe. And again, this is natural because with regular software updates, we kind of know how to deal with them, right? So yes, the service fails once in a while, once a week. What do we do? Yeah. Well, if you use systemd on Linux, you can just ask systemd to restart it, and yeah, your day is done. Right? You can go home. Yes, your service will be operating in a slightly degraded mode. It will crash once in a while, but like especially in cloud environments, most likely your users will not notice it, or you may have some service degradation, but you're still in business. Whereas if the Linux kernel crashes, then nothing works. You don't have a systemd to restart it. You don't have any metrics, monitoring, and it's a complete disaster. So, and the reality is, as I see in many companies, especially like big cloud environments, as well as like even some companies who manage an IoT fleet. Like people just don't like kernel upgrade. They really want to avoid them. And like there, you can see services running on archaic systems like Red Hat Enterprise 6 or something like that, and other scary stuff. But not applying software update is not great, right? And you kind of introduce, by not applying the upgrade, you also introduce your system to some risk, and especially it applies to the Linux kernel. So what do you not get if you don't upgrade your kernel? Well, your bugs are not getting fixed, obviously, right? So, but how many bugs? And let's just look at the data. I will be talking about the different types of kernel releases later in this talk, but so far what you need to understand is like a kernel bug fix release is usually released weekly, on a weekly basis. It's usually Tuesday or Wednesday, and every Wednesday you have a bug fix kernel release. So this graph shows one of the Linux kernel stable branches called 5.15. It's an older branch, but because it has more history, it's like more visible, like the data is more visible here, so you have more data points. And this graph just shows you how many commits per week you get in a bug fix release. So it just counts all commits. And remember, these are just bug fix releases. So these commits are just fixing bugs in the Linux kernel. And we can see that it's actually fresh data. There was another release yesterday. So out of 132 releases on a 5.15 branch, 64, so 50%, have more than 100 commits. So more than 100 bug fixes in a single weekly release. Obviously, 23 have more than 200 commits. And you see these spikes. There are like 10 mega releases with more than 500 commits or 500 bug fixes in a single week release. So imagine if you skip a weekly kernel release. So if you don't upgrade your kernel on a weekly basis, you might have up to more than 500 lurking bugs in your system. And it kind of accumulates each week. Yeah. Right. Secondly, if you don't upgrade your kernel, you might be missing out on huge performance improvements. And we're talking here about the performance in broad sense, not only performance like things are faster, but things are more optimized, demand less resources, etc. So, and here is an example from our production systems when we're evaluating to switch from a 5.4 stable kernel to 5.10. We rebooted some of our canary servers to the new kernel, and we immediately saw the difference that the memory consumption of the 5.10 server is almost like 5 gig less than we had before. So imagine on a huge infrastructure, if you're owning a huge infrastructure and you're saving 5 gigs of RAM per server or per device, if you have a lot of devices, that's a huge cost savings, especially if you run applications in cloud environments. You probably may expect how RAM is expensive these days. And we didn't do actually anything to get there. Like we took what was there already available. So, and basically this was just because in some kernel version, nice people from another company, Facebook, now called Meta, they kind of improved the memory management subsystem in the Linux kernel, and everyone just got it for free just by upgrading the code. Now let's see the same data, like number of commits per bug fix release, but in a different view, in accumulating view. So in this view, we see like 0 release has 0 commits, .1 release has all the commits from one release, so .2 has all the commits from 1 and 2. And then in this view, it's very easy now to calculate the change delta, right? So let's say at some point you want to upgrade from your kernel from 5.15.16 to 5.15.32. And basically your change delta is 2,196 commits, right? Now imagine something happened. You're in the middle of launching a new product and you really need a stable system. So you decided to postpone your upgrade. Postpone for the same time you waited, right? So you 2x expanding the time you wait to upgrade your kernel. And eventually what you will be upgrading to is like 5.15.16 to 5.15.48. And the change delta now is 5,436 commit. Now, if we make the basic and reasonable assumption that the more commits you have, the more commits you accumulate, the more risk you have in breaking something by applying all of those commits. You may also notice that the ratio here is more than 2, right? So, and remember, these are happening weekly releases. So .32 from 16 to .32 passed the same amount of time as from .32 to 48. So you waited twice as long, but your risk of breaking your system by waiting didn't grow twice, 2x. It grew faster in this case. It grew 2.5. So basically, in some cases, the longer you wait and not upgrade your kernel, your risk may grow non-linear, well, linearly, but with a higher coefficient than you would expect. Yeah, so for 2x delaying of the upgrade, we got like 2.5 more risk of the upgrade. Does that make sense? Any questions here? Yeah. Another thing, okay, by not upgrading your kernel, you're not only not getting your bug fixed, you're also not getting your security vulnerabilities fixed. And let's look at the data again. So there is a little bit less data about security vulnerabilities, but still, this graph shows how many CVEs, publicly known CVEs, have been patched in each bug fix release on the 5.15 branch. And you can see out of 128 releases for which data is available, 101, almost 80%, almost each release has at least one publicly known CVE patched. And 33 releases, which is well, roughly like 25-ish%, has more than 5 publicly known vulnerabilities patched in the kernel. By not applying security fixes, you may also risk your compliance. For example, if your device or service is with some reasonable compliance, for example, it processes payment data, you might be subject to PCI DSS compliance, for example. And it says that each publicly known vulnerability in a critical system, and probably a Linux kernel is critical because everything runs on top of it, should be patched within 1 month of release. Who here heard about Equifax story? I see a couple of people. So it's not related to kernel upgrades, but in general upgrades. So Equifax is one of the big 3 credit reference agencies used like in Europe and in the US, and they just didn't upgrade their Apache server. So hackers knew that their server runs with a publicly known vulnerabilities, and they exploited it and like stole some data, and it led to massive scandal, online scandal, a lot of fines, and Equifax is just a too big company, so it suffered a lot, but still stayed in the business, whereas smaller companies may even go out of business just because of that. And remember, 30 days to patch a publicly known vulnerability, which brings us to a fun fact. If your uptime, and because the upgrading a kernel requires a system reboot, If your system uptime is more than 30 days, you're probably vulnerable to something because each release has a publicly known vulnerability patch, right? So someone before here in this room mentioned about like the stable systems which run years. So, and who is older, you might remember like older sysadmin forums where people boasted their server uptime like 4 years, 5 years. So this is not cool anymore. Big uptime is not cool for the Linux kernel. If you have a huge uptime, it's probably bad, especially if your service is talking to the internet. But why upgrading the Linux kernel is so hard, right? And one of the problem that you often encounter in bigger companies, smaller companies, there are general principles and approaches for software update management in production systems. The problem is they don't quite really work with the Linux kernel, but people who are responsible for that process, they're kind of try to reuse that process for the Linux kernel, which brings us to anti-patterns for Linux kernel releases. And the first and foremost, if you want to update something somewhere, the person who is responsible for it, like an SRE, sysadmin, or DevOps engineer, they will ask you like, so why you wanted to upgrade? Like, which things from the changelog is applicable that you want to adapt in your system? And this brings us to this graph, right? So every other release has more than 100 changes. 10 release have more than 500 changes, and they happen weekly. So how huge of a team of Linux engineers do you need to actually review all these releases and say like this commit is actually applicable to our system is not? So you don't have much time, and you will just end up, like counting through commits. It's like, yeah, there is something out there, and you need to do it. So basically, in other words, if the release has 500 bug fixes, most likely there is something out there which is applicable to your system. So don't ask that question, just take the bug fix release and apply it. Similar questions when you want to upgrade for security reasons. Is this security? So like you say you want to upgrade, there is a CVE patch, but then you get asked like, oh, but are you sure this security vulnerability is actually exploitable on our system? And this is probably a correct question to ask, but we're asking for the right people, wrong people, right? So who can definitely answer this question correctly? It's probably the attacker, because sometimes the security vulnerabilities are really hard to exploit. They require a lot of effort and dedicated knowledge, but the attacker is motivated to do so because they want to break into your system. This is their main bread and butter, so they will spend exclusively 24/7 just to design a successful exploit if they know you have a known vulnerability in the system. And sometimes you may even see, the attacks get really sophisticated, so sometimes you can see a system compromise which was compromised by not having a major security vulnerability, but the attacker was somehow cleverly chain like 5 minor security vulnerabilities together to design a successful exploit, right? So this is the attacker. An attacker knows if our system is exploitable. But we don't ask the question from the attacker, right? We don't know who they are. We ask like a security patch reviewer, which has different priorities. They want to go home on time, right? It can be a security engineer or a Linux engineer or some SRE or DevOps. And probably they need to review several patches a day. And remember, we have these 100 commits, 500 commits. And they may have other competing priorities. Security engineers are often tasked to do like security tooling, design policies, et cetera, et cetera. So it's a kind of like you're asking this person. And that person will spend like roughly 5 minutes looking at the vulnerability to give you an answer. But will that answer be correct? Probably no. Another standard practice in software upgrades is soaking. So let's just say, like before the upgrade, let's put it into some small subset of production, which we'll call canary, and just let it sit there for 1 month to ensure like nothing breaks. But again, the problem here is the more you soak it in canary, the more you're not putting it out into production, and then you kind of start accumulating your challenge delta in production, and your risk may grow faster than the amount of time you delay. By soaking for too long in canary as well, you're not patching known security vulnerabilities. So your system again may run with known security vulnerabilities, and like you may be breaking compliance along the way. So remember, 1 month to patch a security vulnerability, but you're soaking it only for 1 month in canary, so you're obviously breaking this requirement here because you're not putting out the kernel into production. And if we look closer, what does like soaking mean? Why do people say let's soak? It probably means we kind of don't know what to look for. So we do like metrics of observability or some tracing or debugging support in our service, because we can't put it on a new kernel and say if it's healthy or not by looking at some data, right? So we just wait for something to go wrong. It might mean also we just don't know what our workload. Like I often get questions like, will the kernel upgrade break my workload? And like we'll run dozens of workloads. Some of them like care more about like the performance of the file system. Some care about like the scheduling latency in the kernel. Some care about like I don't know, something else, networking, etc. So how can I answer this question is I'm not sure what your workloads actually require. So workload owners should actually understand their workload and say like, like I'm a database and I really care about the performance of the file system as well as the system page cache. So are there any potential breakages in those specific subsystems which may impact my workload? And probably high soak time means lack of sufficient pre-production kernel testing. So if you know what you're looking for, you probably can test for it. So you can write unit test, integration test, performance test, etc. And just make a decision immediately if the upgrade breaks it or not. Final argument which you usually get, especially in some companies, is like, kernel is just a critical component, so let's have more approvals before deploy. So for regular software release, you need to have 1 approval, but for kernel, you need to have 3 approvals or 2 approvals, right? And again, this is kind of related to our perception that this kernel is more that like big monster which can destroy our universe. It's just too risky. But what if I told you today that the kernel deploys are inherently safer than any other software? Would you believe me? So this is a Cloudflare network. I don't know if you see the globe here. Somehow it's not visible, but there is also a planet but the gist of this is like we have a lot of data centers across the world, right? And all these dots are some cities on the world map, and even each city can have more than 1 data center. And we continuously deploy software there all the time. Of course, we can't do it manually, so we have automations for that. So what is like a regular software deploy looks like in Cloudflare? So engineers update the code, compile it, package into our package repository. We use Debian. So they upgrade the software package. Then the production system sees that a new package is available and it's allowed to upgrade. So it just grabs the package. If it is a service, it can restart the service. It can be graceful or non-graceful. But the idea is once we push the package and allow the upgrade, that code, which can be buggy, can propagate across all that network in minutes. And without proper safeguards, and we actually learned it the hard way, if you push the change too fast and it's bad, you can all have a global outage, right? You can completely shut down your whole network. And we have had some big outages in the past, and with public blog posts, you can read more about them. Whereas for Linux kernel, the biggest disadvantage or advantage is to upgrade a kernel, you need a reboot. And rebooting a server, it's kind of like not an instant operation. So we need to drain traffic from the server. We need to disable it from production systems, silence the alerts. We need to actually reboot. And if you reboot at a modern server, it doesn't reboot quite fast. It kind of takes minutes. Then when it's up, we need to wait for it to contact our configuration management system, get its configuration reconfigured. Once the server is configured, it runs acceptance tests that it's ready to join the production. And finally, it joins the network again and starts serving traffic. And the idea is like, because you have to do it, you can't do it instantly on all the servers, right? So because you will just break your system. So we do it in small batches, like 1 by 1 in each data center, or 2 by 2, so users do not get performance hit. Right? So because you can't do all the servers at once and you need to reboot them, so the kernel release to production without any additional safeguards is still inherently slow-paced, gradual rollout. And if we accidentally release the build kernel, we will have plenty of time noticing it, because yes, 2 servers didn't boot properly. We investigate, see, oh, the kernel crashed, so it's probably not a good release. We stop the release and job done. So users will not notice it. So are you convinced now? Another problem with Linux kernel releases is that people not deeply familiar with the kernel itself are not really familiar with the kernel release process, and they just treat every kernel release the same way and try to apply the same management policy, where actually releases are different. So how kernel releases are designated? So you have a number, a dot, another number, a dot, and another number. So for example, 5.15.32, right? And who here is familiar with semantic versioning? Oh, everyone, cool. Yeah, so it does look like semantic versional, but one thing you can take away from the talk, it's not a semantic versioning system. So this versioning was there before semantic versioning, it was even proposed, so even though it looks like it, it's not a semantic version. Instead, what it means is the first 2 numbers is the major version. So, and it's not kind of like in semantic versioning, it's not major and minor. So the major version can have new features or complete subsystem rewrites. The last digit designates, similar to semantic versioning, only bugs and security fixes. So in this case, when you just bump the minor version, you will never get new features or subsystem rewrites, only tweaks in code which fixes bugs or security vulnerabilities. So let's see how the kernel development process works in a nutshell. So the main code for the Linux kernel is contained in Git or JIT, and this repository is solely controlled by Linux dictator Linus Torvalds. But then you have development branches for different subsystems. So for example, you have a subsystem for drivers, you have subsystem for memory management, and you have subsystem for networking, and new features are developed there. And at some point, they call it the so-called merge window, Linus goes and pulls new stuff from these branches to the main branch. And at some point, when Linus decides that the kernel needs a stable release, he creates a stable branch, which is designated by these two major numbers. So you have like 5.10, 5.11, 5.12. And this happens roughly every 9 to 10 weeks. And then from the stable branch, you get these bugfix releases, which are applied by tagging. So you tag a bugfix release 5.11.1, etc. But how a bug? We said that the bugfix releases never get new features. So how are they, like bug fixes are propagated? So if you find a bug fix, you don't, sorry, not a bug fix. If you find a bug in the Linux kernel and you have a patch for it, you don't go and commit it to a bug fix or to a stable branch or a bug fix release. You still need to go and talk to the subsystem maintainer and present your fix there. And this is done to ensure that your bugs is not only fixed in stable releases, but also in the upstream code, development code. So you basically create a patch, you submit it to the respective subsystem maintainer, and eventually that patch gets merged to the main branch for Linux Torvalds. But these bug fix commits, they are specifically marked to be bug fixes, and therefore, at some point, the stable branches cherry pick those bug fix commits to the stable branches. And when enough bug fixes or security fixes are accumulated, sometimes when you need an urgent security fix, it happens instantly. So the stable branch maintainer creates another bug fix release, and this, as I said, happens roughly every week. So, as I mentioned, a new major or stable kernel version is released every 9 to 10 weeks. And the merge window, which I said, where Linus can pull new features into his main branch, is only 2 weeks usually. So it's 2 weeks for development and 7 weeks for bug fixing. So still, even like the bleeding edge Linux gets a lot of testing. The other thing which is confusing to many people who manage kernel upgrades, that the leftmost number, version number, means nothing, right? So a major upgrade from 4.19 to 4.20 can have same amount of even more new features than the upgrade from 4.20 to 5.0. So, and this is what confuses most of the people who are responsible for production systems. They say like, oh, we used to upgrade from 19 to 20, but we're now upgrading from 20 to 5.0. This is probably a super mega release. We have to really thoroughly test it and soak it. No, it's no different from the previous upgrade. And how Linus says about this, he increments the leftmost number when he runs out of fingers to count the middle number. But for whatever reason, sometimes he increments this number after 21, and sometimes he increments this number after 19. So he has some kind of variable number of fingers. So yeah, I don't know, but whatever. He's a dictator, and he solely decides when to increment this leftmost number. And yeah, and bug fix and patch releases are released once a week. They are denoted by the rightmost version number. They're usually cherry-picked from the main Linux branch, so you don't get new features. And you don't get new features, and therefore regressions are really, really rare. So now in Cloudflare, we just continuously apply bug fix releases, and I don't remember any regressions we see in years. I mean, we didn't expect. There were performance regressions for the recently disclosed CPU vulnerabilities. So Linux kernel implemented a mitigation, which was known to have a performance impact, so you get a performance regression. And yeah, the bug fix releases may contain critical security patches, and therefore, because there is so lot of them, there is almost always something which is applicable to your system, so you almost always want to apply them. Uh, but what about major releases, right? You still should want to get new features like the memory management subsystem rewrite I mentioned earlier, right? So the stable branch is capped around 2 to 3 months, and at that point it's declared end of life. So stable branch capped means bug fixes are backported there, security patch. But then at some point it's declared end of life and you don't get any support. And at this point you're just encouraged to move to a new major version, but obviously because you need to more thoroughly test it because it has features in it, so it might be too expensive, right, to test a new kernel release every 2 to 3 months. So if this is the case, so there are so-called long-term stable releases for which our bugs and security fixes are backported for at least 2 years, but some branches live for 5 years or more. And it's usually the last stable release of the year. Therefore, we can say a new long-term release is roughly available every year. And it basically provides you with enough time for more rigid evaluation of the next long-term release. So if, evaluating a new major kernel is too costly every 2 to 3 months, you can just follow the long-term releases and you can evaluate new kernel up to 2 years, but the advice is doing it once a year. Yeah, so if you're interested in more details learning about the kernel release process, there is actually a good page in the kernel.org, which probably no one reads, and it explains all these version numbers and stuff. Okay, so this is kind of like, let's summarize what I discussed today. And so how do you do safe and easy production kernel upgrades? First of all, don't create a dedicated deploy process for the Linux kernel, because kernel updates are usually less risky than any other software, and a simple stage rollout is usually enough, and kernel releases are naturally slow-paced because they require a system reboot, and you always have a lot of time, headroom to notice that a bad release went through and just stop the release. Secondly, avoid justifying a bug fix kernel release upgrade. Kernel is probably the biggest open source project in the world, and there is always something which may be applicable to you. So you should just apply bug fix kernel releases with no questions asked. So because there is almost always there is something, there are so many of them because there is almost something which is applicable to your system, and the regressions are quite uncommon. And you should probably minimize your canary soak times and use metric. Try to think about what kind of additional metrics of observability you can add to actually determine if a kernel upgrade is healthy just by as fast as possible. Yeah. Do try to upgrade merger kernel releases because you will probably get new features and optimizations. But if it's too costly, you may stay on the long-term branch, so you get at least 2 years of support for bug fixes and security vulnerabilities. But again, don't wait for these 2 years to pass out because probably your evaluation process is long. So start evaluating a new long-term release after a year, and you will get more features and better performance or resource utilization. And also doing it more often again will minimize your change delta. If you don't have it, implement. If you have it, improve pre-production testing for major kernel validation. Try to understand your workload, write tests which exercise a specific kernel subsystem which are applicable to your workload. And it also can really help when communicating with the Linux kernel community, because there is a general perception that the Linux kernel community is not receptive or sometimes rude. But on the other hand, if you come to them and say, hey, my server is misbehaving, and like the response, if you get a response even it will be like, so what? Okay. And say like, oh, I run X, Y, Z, and then you have to install Oracle and then like populate it with our production data, and then you will see the issue in the Linux kernel. So the upstream community cannot help you with that. So instead, if you say, hey, I developed this small test or reproducer which shows a kernel regression, if you provide that, you would immediately, always get a really like positive feedback and response, and your issue will be fixed. Because kernel is just too huge to be an expert in everything, and many times in my experience, like even though I work on the Linux kernel, I don't know other some kernel subsystems, but I do have a clear reproducer of the bug. I just spit it out to the mailing list, and somebody from the mailing list comes, aha, and like the issue is fixed in one day. And do make metrics-driven decisions if to apply upgrade or don't, and not time-based soaking decisions, right? So I can see some policies like, oh, we need a canary uptime of at least like 2 years to justify the kernel upgrade. Also, metrics monitoring and deploy automation can help with human risk perception. And this is what we learned in Cloudflare as well, that there is still this inherent perception of kernel being too risky. So before, when we had manual kernel upgrades and you task it with a new engineer coming into the company, they become just scared, you know, like, oh, it's a kernel. Do I upgrade the kernel on the whole Cloudflare network? What if it fails? I'll be blamed. So now the process is fully automated. Our SREs sometimes, many times, do not even know that the kernel upgrade is happening in the system, because the kernel is compiled, it's tested, it's being rolled out by some CI/CD pipeline, and we only get notification if something is broken. But generally, you don't have to ask people to do, I wouldn't say risky, but operations which they perceive as risky. So like automating and you'll also, and if somebody asks, if you have metric, you say, you can always back up your data saying like, look, this release look healthy, don't worry. So short summary, Linux kernel upgrades are not more risky than any other software. You do need to patch early and patch often. And you do need to apply the kernel bug fix releases with no questions asked. And you also try to understand your workload metrics and implement metrics and monitoring. And if you have all that, your systems will eventually stay patched and more secure. Thank you very much. That's all I wanted to say for today, and I'm happy to answer questions. Yes? Mm-hmm. So the question was, ksplice, is that the equivalent of doing reboot? Ksplice is the technology which can apply patches to the code without the needing as a reboot, right? Yeah, so there were actually two competing technologies. It was ksplice and LifePatch, or they're the same thing. I don't remember exactly. But I generally don't recommend both of them. And the reason being is it becomes like more of a marketing tool for enterprise Linux distribution than it is useful. So we are all like low-level developers here, and you should understand that to live patch a live code, so what it basically does, it loads new code into the kernel space and routes the calls to that code from the old code, from the new code. And that can only work in some very small cases where the patch is in the logic. But what if the patch requires you to modify a structure? And if you go and modify a structure, like let's say you lack synchronization somewhere, so you need to insert a mutex to a structure, right? So you change the structure, and the rest of the Linux kernel code doesn't expect the new structure layout. So your system will obviously break. So live patching is very, very tricky. It's very hard to get right. And that's why it's mostly got right by like paid Linux distributions, because they invest a lot of effort in it. And it doesn't cover all the cases. So if for all that effort, you can rather invest making your system very easy to reboot, and you're set. Any more questions? Going once, going twice. Okay, thank you.